So we've been careless somewhere. There's something we don't quite understand properly. We thought we understood that if we have two coherent states and we drop them on a detector, we'll see fringes. And we thought we understood that if we have two number states and we drop them on a detector, we won't see fringes. But then we realized that a mixture of coherent states with different phases is exactly the same thing as a mixture of number states with different numbers, and therefore they should give us exactly the same results for all experiments, no matter what. So one of those statements must be a little bit wrong. So if we look instead at what we actually calculated, we show that the fringes turned up in the expectation value of the density, and the lack of fringes turned up in the expectation value of the density. That tells us that if we do this experiment many, many times, then in one case we'll see fringes, and the other case we won't see fringes. Now, of course, the actual placement of those fringes depends on the relative phase of our two coherent states. So if we really did have this mixture where we had all the different phases of the coherent states, then on each particular occasion we might get fringes, but on average this expectation value would actually wash out. So this calculation up here was for a particular pair of coherent states, and over a large number of runs of that experiment with different phases, we would actually expect to see all the phases washed out. So that's not so surprising or strange. So now we're coming down to this situation where what happens with the number state? Well, we know that with a number state, if we have a pair of number states, on average we're going to get something that's all washed out. But what this is suggesting down here, that equivalence, is that actually each time we do the experiment with a pair of number states, we will in fact get fringes. Now how does that work? So our measurement of dropping these atoms onto the detector and looking for fringes is essentially a measurement of phase. We're trying to see if there's a phase between the two condensates. Why are we suddenly getting a phase if we start off without a well-defined one? Well, actually, measurement works like that in quantum mechanics. If I have a wave function and I measure where it is, if I measure where my particle is, even if it has a broad wave function, after I make my measurement, it's become really localized. If I have something in a superposition of different spins and I measure its spin, it suddenly jumps to a particular spin. So if I have a pair of BECs and I try and measure their relative phase, they're going to get a relative phase. So what that means is, to understand how the system really behaves, we're going to have the measurement process in our model. That's a really important part of it. So our density matrix, we know how that's going to evolve. So we had the Hamiltonian evolution, but we also have the interaction with our detector. And the interaction with our detector is going to add terms to this master equation, and it's going to remove particles. So if it's going to remove particles, we're going to expect to see a term something like this. So that's a decoherence operator that's going to remove a particle at position x, and of course we can't have a special position x, so we'll integrate over, and we might have a constant as well. So that's a likely master equation for the average behavior of dropping atoms down onto a detector. But we don't actually want the average behavior, because on a given measurement run we're going to get a particular measurement result. And so those detection events are not going to happen averaged over all those positions. On any given run, they're going to happen at particular positions. So we can see immediately why, on average, we don't see any particular fringes in the coherent state if we're averaging over all the phases. Averaging over all the phases means we're going to get a blurred out fringe. And so we never expected that even for the individual shots of writing the density matrix as a bunch of number states. I guess the surprising thing here is that if we have an individual coherent state, we expected to see fringes. So we'd expect to see fringes on each individual run. And what that means is we should expect to see individual fringes on each run in this expansion as well. And in fact, expanding out exactly what the conditional master equation does for individual clicks on our detector will show us that as well. So the only remaining question is, what did the experimenters do wrong? They seem to have got the wrong answers. We expected to see fringes in the superfluid regime, but we should have expected to see fringes in the mod-insulator regime as well. Just because the sites all had number states in them doesn't mean we shouldn't have seen fringes. So why aren't there fringes there? And the answer to that is a particular detail of the experiment, which is that they were using a three-dimensional lattice. And their three-dimensional lattice was giving us a diffraction pattern. In this regime, in the superfluid regime, it's giving an interference pattern that was the same for each layer. And all of these layers were dropping down onto the detector and giving us this pattern and reinforcing each other. But in the mod-insulator regime, we were getting a fringe with a random phase, and each layer had its own random phase, and when we drop all of those onto the detector, it all washes out. And so if that's true, then we should be able to see the fringes in both regimes if we do the same experiment in one dimension with a one-dimensional lattice. So this was done in Jean Dalabar's group in Paris, where they got a one-dimensional set of traps for the BEC just by changing their laser geometries. And then when they expand their lattice, they get their interference fringes as a series of blobs like that. It's just one series rather than a whole bunch of overlaid ones. And our new enlightened intuition tells us that the visibility they get should not depend on whether they start with a superfluid state or a number state. So whether in the Mott insulator regime or the superfluid regime. So it shouldn't matter on how high they make those potential barriers in their lattice. And so what we get is something like this. And what we're drawing here is we're drawing the visibility on this axis, so it's a polar axis. So if you have a point out in the circle here, that means you've got beautiful perfect fringes with total contrast. If you have zero visibility in the middle, that means you have something washed out with no visibility whatsoever. And what our angle axis is, it's which actual fringe position we have. So if we have fringes like this, that's one angle, and that gives us a phase, or we might have fringes like this, in which case we get a different phase. The important thing here is if we start in the superfluid regime, if we start from one condensate and break it into two, then in fact we should have complete control over that relative phase. And when we drop them back together again, we should see that particular fringe spacing we were expecting. Indeed, this kind of control is essential to all the precision measurements that people do with atom lasers now. But you'll note that in the Mott insulator regime, the actual distribution of visibilities is very, very similar. It's basically indistinguishable from the visibilities we have in the superfluid regime. You can see that there's no real tendency for the Mott insulator regime to be washed out and in the middle. What we have instead is we have a tendency for it to pick the phase completely randomly. Whereas in the superfluid regime, with a bit of care, they can make sure that they pick the phase with some kind of control, depending on exactly how they split apart the BECs in the first place. And so now we can see that if you do the experiment with enough control to see all the fringes and really know where they're coming from, then in fact a mixture of number states and a mixture of coherent states with unknown phase are indeed exactly the same thing and behaving the same way in the lab. There are two morals to get from this story. The first is that the way you break up a density matrix into different bases is not unique. And because it's not unique, you shouldn't take it too seriously. If you happen to be able to diagonalize your density matrix and say, this is a mixture of these things, that's fine. That will accurately predict everything you might see. On the other hand, you mustn't believe that it really is exactly a mixture of those things, because you could equally well say it's a mixture of other things, and that would be equally true. And the second moral we want to take is that measurement is a very important part of the process in quantum mechanics. And if you really want to talk about things like feedback control of quantum systems, or if you really want to talk about what we really see in the lab, you actually need to have a full theory of what measurement is doing in a quantum system.